Move a magnet through a coil of wire, current flows, you can measure it. Hook up a voltmeter, watch the needle jump. Stop moving the magnet, current stops. Move it again, current again. Why does motion create electricity? What's different when the magnet moves versus when it sits still? The magnetic field is there either way. You can feel it pulling on another magnet, on iron filings. So what does changing do? Why doesn't a stationary magnet sitting right there in the coil with its field filling the space create any current at all? Everyone says a changing magnetic field induces current. That's just describing what happens. That's not explaining it. That's like saying fire burns because of combustion. The real reason involves something nobody talks about, what electric and magnetic fields actually are to each other. It's not about the field changing. It's about what an electron sees when it's sitting in a wire and a field sweeps past it. And so everyone gives you the circular answer. Changing magnetic flux induces EMF. Okay, but why? Because of Faraday's law. That's just naming it. That's not an explanation. Faraday's law tells you that it happens, and it even tells you how much the voltage equals the rate of change of flux. But it doesn't tell you why the electron feels a force. It doesn't tell you the mechanism. You could write down F nHma too, and that tells you how much acceleration you get from a force. But it doesn't tell you where forces come from. So we're stuck. We need to go deeper. We need to ask, what's actually happening when the magnet moves? Forget the magnet for a second. Think about an electron. It's sitting in the wire, just sitting there, not moving. The wire is stationary. The electron is part of the metal. It can move through the metal, but right now it's not. Now the magnet sweeps past. From the electron's perspective, it's just sitting there, minding its own business, and a magnetic field is moving relative to it. Moving relative to a magnetic field. And here's the key thing, the thing textbooks bury in equations. If you're sitting still and a magnetic field moves past you, that's the same as you experiencing an electric field. Wait, what? How can a magnetic field become an electric field just because of motion? This is the weird part. Magnetic fields and electric fields aren't actually separate things. They're two aspects of the same thing, and which one you see depends on how you're moving. It's like, imagine you're standing still and a train passes. You see the train moving, you're stationary. From the train's perspective, the train is stationary and you're moving. Motion is relative. Nobody's absolutely at rest. Same thing with fields, but stranger. If you sit in a magnetic field that's moving, you experience an electric field. If you move through a magnetic field, same thing. Well, not exactly the same. The math works out a little differently depending on which is moving, but the basic idea holds. The point is, motion changes what kind of field you experience. But why should motion change what kind of field you see? Okay, in the 1860s, James Clerk Maxwell was playing around with the equations that describe electricity and magnetism. People already knew that electricity makes magnetism. Ørsted discovered it. Ampere worked out the math. Electric current through a wire creates a magnetic field around the wire. And people knew that changing magnetism makes electricity. Faraday discovered that in 1831. But Maxwell realized these aren't separate forces. They're two aspects of one thing, the electromagnetic field. What you call electric versus what you call magnetic depends on your state of motion. Charged particle sitting still? It makes an electric field only. Same particle moving? It makes both an electric field and a magnetic field. The field itself is the same field. It's just that different observers, moving at different speeds, see different. Mixtures of the electric and magnetic components. The field is the field. Electric and magnetic are just names we give to components based on our reference frame, like left and forward depend on which way you're facing. So, magnet moves past wire. The electrons in the wire see the magnetic field changing, getting stronger as the magnet approaches, then weaker as it passes. But from their reference frame, that changing magnetic field also shows up as an electric field appearing. And electric fields push charges. Electric fields exert forces on electrons. The electrons get pushed along the wire. That's your current. The changing is really just motion-induced transformation between field types. The magnetic field sweeping past looks electric to the stationary electron. But wait, here's something deeper that standard textbooks skip right over. They say, changing flux through the loop creates EMF around the loop. They draw pictures of field lines, count how many pass through. The loop, take the rate of change that gives you the voltage. All true. But here's what they don't explain. Why does the electron care about the total flux through the loop? The electron is localized. It's right there in the wire at some specific point. How does it know about the flux through some imaginary surface you've drawn inside the loop? How does it sense what's happening over there, a centimeter away? Answer, it doesn't. The electron doesn't care about total flux. What the electron experiences is completely local. The force on it depends only on the fields right where it is, at that point in the wire. Here's the real picture. As the magnet moves, the magnetic field strength at each point along the wire changes. That changing field from each electron's local perspective appears as an electric field component pointing along the wire. The electric field pushes the electron. Every electron around the loop experiences this. Add up all those local electric field contributions around the entire loop, that gives you the total EMF. It's a sum of local effects, not some spooky global knowledge of flux through surfaces. Faraday understood this actually. He thought in terms of lines of force being cut by the wire. He was thinking locally, the wire cutting through field lines, each part of the wire interacting with the field right there. Later, physics teachers abstracted it, made it about flux through surfaces and Faraday's law, written with Dell operators. Lost the physical intuition that Faraday had. Let me prove it to you. Take a homopolar generator. This was Faraday's original design from 1831, actually. You take a metal disc and spin it between the poles of a magnet. The magnets are stationary, fixed in place. Connect a wire from the center of the disc to the edge through a sliding contact. Spin the disc. Current flows. You can light a bulb with it. But here's the kicker. The magnetic field isn't changing. The field is static. The magnets aren't moving. If you draw any surface you want and count the flux through it, the flux isn't changing. Zero rate of change. According to the simple changing flux creates voltage story, there should be no EMF. Yet current flows. Why? Because the disk is moving. The electrons in the disk are moving through the magnetic field. A moving charge in a magnetic field experiences a force, the Lorentz force. That force pushes the electrons radially, from center toward edge. That's your EMF. Same phenomenon, but now it's obvious that it's about relative motion between charges and fields, not about some abstract flux changing through imaginary surfaces. And here's where it gets strange. That transformation between electric and magnetic fields, the mathematical rules that govern how motion mixes them, those are exactly the same transformation rules Einstein used for special relativity. The speed limit built into Maxwell's equations. The speed at which electromagnetic waves propagate is the speed of light. Maxwell calculated it in the 1860s from his equations. He got 3 times 10 to the 8th meters per second. That was the measured speed of light. Wait, people said, is light an electromagnetic wave? Yes. Light is oscillating electric and magnetic fields propagating through space. The fact that moving magnets make electricity and the fact that light exists and travels at 186,000 miles per second, these are the same fact. They both come from how electric and magnetic fields transform into each other. And that transformation structure is what Einstein built relativity on, which raises a question we've been dancing around. What is a field anyway? We keep saying field, but what is the substance? Honest answer, we don't really know. We can describe what it does. Charges create it. Charges respond to it. It carries energy, real energy. You can measure it. It carries momentum. You can bounce light off a mirror and measure the tiny push from the light's momentum. The field propagates at light speed. But what's it made of? I'm sorry, but I can't explain it in terms of anything more fundamental. It's one of the basic things the universe is made of. Like asking, what is an electron made of? Far as we know, nothing. It's fundamental. A field is fundamental. Nah, you can't build it out of something simpler. When you ask, why does a changing magnetic field make current, you're asking about the relationship between aspects of something fundamental. It's like asking, why does moving create velocity? The motion is the thing. Or, better way to say it, asking why the fields transform between electric and magnetic components is like asking why space and time mix when you change velocity. They're part of the same geometric structure. Space-time, or in this case, the electromagnetic field structure, that's just how the universe is built. Of course, every generator on Earth uses this principle. You spin coils in a magnetic field, or you spin magnets near stationary coils. Same thing. Continuous change in what the coils see, continuous current generated. Your power plant. Steam spins a turbine. Turbine spins coils through a magnetic field. Electricity flows out to the grid. Your car alternator. Engine belt spins a magnet assembly. Stationary coils see the field changing. Current charges your battery. Typical big generator spins at 3600 RPM, that's 60 revolutions per second, 60 Hertz. The coil sees a north pole, then a south pole, then north again, 60 times per second. The field direction flips 120 times per second. That's your AC current, alternating because the field change reverses direction as the magnet rotates. You could make DC with a commutator that switches the connections, but AC is easier to generate and much easier to transmit over long distances. Hook up an oscilloscope to a hand crank generator, spin it slow, you see the voltage wave up and down smoothly. Spin faster, the wave oscillates. Faster, frequency increases. Push harder on the crank, more torque. The wave gets bigger amplitude, more force on the electrons, higher voltage. So circle back to where we started. Move a magnet, current flows. Why? Real answer, because electric and magnetic fields are two views of one underlying thing, and motion rotates between those views. The electron in the wire experiences a force because from its perspective, the sweeping magnetic field has an electric component. That component pushes it. That's as direct as the explanation gets without writing out the full tensor transformation math. But this bothered Einstein when he was a teenager, around 1895. The textbooks gave different explanations depending on whether you moved the magnet or moved the wire. Magnet moves. Changing field induces EMF in stationary wire. Wire moves. Electrons moving through field experience Lorentz force. Two different explanations, but the exact same result, same current either way. Einstein thought, that's suspicious. The physics can't depend on which one you call moving. There should be one explanation. That insight led him toward relativity. The fields transform. The underlying electromagnetic reality is the same. It's just a question of reference frame. Are you moving with the wire or with the magnet? Electromagnetic induction is actually a window into relativity. The symmetry of the phenomenon, move magnet past wire, same as move wire past magnet, that symmetry is built into the structure of space-time itself. We started asking why changing magnets create electricity. We found the answer because electric and magnetic fields are two aspects of one thing, and motion rotates what you see. The electron experiences a force because from its perspective, the sweeping magnetic field has an electric component. Why do the fields have this structure? Why does the universe use these specific transformation rules and not some other set? That's built into the geometry of space-time itself. Einstein's equations tell you the transformation rules. Maxwell's equations tell you how the electromagnetic field behaves. But why those equations? That's a different story. At some point, you hit bedrock. These are the rules the universe runs on. We've tested them. They work. GPS satellites depend on relativistic corrections. Particle accelerators depend on the Lorentz force. Generators pump out exactly the voltage predicted. The equations match reality to ridiculous precision. But explaining why the universe chose this structure over some other, I've got to stop somewhere. That's philosophy, or maybe it's a deeper physics we don't have yet. The deeper you look, the more you realize electricity and magnetism are shadows, two-dimensional projections, of something stranger living in four-dimensional space-time, and we've only scratched the surface.